All right, so this, I chose the matrices and linear transformations video to kind of do the conceptual review. Hopefully you find this useful. My name is Charlie, and this kind of became longer than I expected it to be, more because matrices and linear transformations are so vague and have many applications, both related to electrical engineering and not. So the contents, I'll just briefly go through it so we can have some sense of organization. First, I'm going to define what a transformation between vectors is, and then also what makes it linear. And I'm also going to give a geometric visual approach from like Rn to Rm, which we'll talk about later, what that means. And usually I'm going to do R2 to R2 since I can draw that on paper. And then we're going to talk about how do we make this an explicit mathematical description, because you want to define this operation and tell exactly what you need to do. So what we do is we using matrices, and then I'm going to talk more about like some operations you can do with them, some properties of these operations, and talk about some special matrices. And then we're going to have a new kind of insight on matrix multiplication, and now we can show that this can be explicit mathematical description of linear transformations. So in order to do that, we have to prove that every matrix multiplication operation is indeed a linear transformation, and we also have to prove that every linear transformation between two vectors can be represented as matrix multiplication. And then finally, I'll give some examples. These aren't entirely related to like electrical engineering, but they're related to related fields such as geometry, like if you want to create, as in the midterm, a robot that moves a certain direction. And the PageRank algorithm is very similar to the pump problem, so we'll go over that. So what is a transformation? Well, it is, first of all, just a function where there's an input and output as usual functions. We're used to real valued functions such as fx equals x squared, where you take in a real number and you output a real number, or just take in anything and output a real number, but we're used to this kind of function, right? And then, well, there's three things that every function has, like the domain, which is what it can take in to have it still be defined. Basically, what this means is all possible inputs, and then codomain, which means like what type of function are we dealing with. In this case, real value function means that your codomain must be the set of all reals. So x squared takes in all reals, and the codomain is all reals. And then the range, which if you like look at the actual function, you're going to see what does it actually output. And in this case, you're going to have f of x is greater than or equal to 0, since no square is negative. Similarly, transformations of vectors are also like functions, or we can think of them as mappings. You're taking in a vector and you're outputting a vector. So what is the domain? In this case, we're going to call a vector, and we're going to say it's part of Rn. And since we're dealing with this in the concepts of data and the context of like measurements and numerical measurements, this will typically just be Rn, because these are real number measurements and there's n of them, so a set of n of them. That means it's part of Rn. And then the codomain is going to be Rm, meaning this is what you're going to get, and this is like all, like you can expect some vector like this even before analyzing what this transformation actually does. And this just is the same thing. It's a set of data with m reals. And range is, if you look ahead to the vector spaces one, it's just if you can represent the transformation as a matrix multiplication, AV, where A is a matrix, then the range is going to be equal to the column space of A. And we'll get into that a little bit. So let's also define linearity. So basically what that means is it just satisfies these two properties, that Ta plus b is equal to Ta plus Tb, and T times scalar, T of a scalar times A is equal to, you just can pull this scalar out and then multiply by that transformation. So let's just give some visual basis, since I like to talk talk about things approaching it in a visual manner first. So yeah, I'm just taking some vector here, applying a transformation. Now look, it's over here. This is R2 to R2 since it stays on this plane. And then the special transformations, for example, like rotation, I take these two right here and I rotate it by theta degrees. And another one is reflection, where the angle with respect to one line remains constant, but you go onto the other side of it. That's reflection. So here is the reflection over the x-axis. All right, so now we're going to talk about how to mathematically describe this. And this means we want explicit definition so we can give exact mathematical operations so that we can always have some expected outcome. And for this, we're going to introduce the concept of matrices, which should have been introduced in previous ones to describe system of equations, but I'll go ahead and do it again. So you have m rows and n columns, and the first one is 1, the first row is 1, they go left to right, and then the columns go vertically. So Aij, subscript ij, right here, just means the, just one item. So you as a two-dimensional array in Java, or just, you go onto some row, and then you go along it to some column, and then that's your value. So then this is kind of just a general expansion. So you can just think of it as some set of data as well, just like a vector, but we care also about some amount of dimension, which is why we don't put it in one line, but as a, as a grid. So we're going to call this an m by n matrix since it has m rows and n columns. This is the standard. We use letters m and n as well. Those are standard. So just some basic operations. Scalar multiplication of a matrix, CA, which means you multiply every term inside the matrix by that same scalar. So that should be intuitive. And then some properties are, two scalars multiplied by each other times A is, you can associatively change that. So that's just associativity of multiplication within the reals, since you're multiplying real numbers inside the matrix either way, and we can use this property. And then you can do like alpha plus beta, or scalars times A is alpha A plus beta A, which is just distribution of multiplication, which is also a property of the real numbers. And since everything here deals with direct one-to-one correspondence with the terms, we can just use properties of real numbers directly instead of like vectors or matrices. So yeah, let's just do an example. 3 plus 2 times 1, 1, negative 1, 1. Well, that's, if you first do it the regular way with PEMDAS, you do 5 times this matrix, which gives 5, 5, negative 5, 5. Or you can distribute, which gives us this, 3 times 1, 1, negative 1, 1, plus 2, 1, 1, negative 1, 1. How do we do this? Now we're going to introduce another operation, which is matrix addition. Basically, you just add corresponding terms, but here you also must be careful that the dimensions of the matrices match. Otherwise, it is not a defined operation. So that's basically the general form. And its properties are commutativity. This comes from commutativity of the reals in addition, since you're adding corresponding terms, which are reals. And then associativity, which is A plus B plus C equals A plus B plus C, which follows the same strain of argument. And then if you put some constant to A plus B, you can distribute that constant as well, which is just distribution of, it's just a distributive property. So yeah, let's just keep on going off that old example. And now we can add these, we can do some scalar multiplication as we see right here. And we can just add these to get this right here. So then this 5, 5, negative 5, 5 is equal to what we get from this initial calculation. So this property checks out for this example, and we already kind of can prove it in general. It's just that this is some example. And now some more properties. A plus 0 matrix is A. We call this the additive identity, and 0 is just a matrix with all elements are 0. So we can just adjust this dimension of the 0 matrix to fit that of A so that the operation of addition can be defined. And then A plus negative A, which is A plus negative 1 times A, is 0, and this is the additive inverse. And you can just see this by distributing negative 1 into the terms and just one by one seeing that they all sum up to 0. And some other properties of matrices. I'm not going to go into too much about some physical meanings and examples because I'm mostly focused on and concerned with transformations. But there's also transpose where you kind of just flip the rows and the columns such that the ijth element of the transpose is the jith element of the original. So let's just see an example. The transpose of this matrix, 2, 1, 1, 3, 0, 3. Well, now first of all, we have to see kind of that if here's an m by m matrix, then you're going to get an n by m matrix, and here's 2 by 3, so you're going to get 3 by 2. So let's just have this idea that you're going to fill in 3 by 2 first, and then you just kind of go, well, A transpose 1, 1 is A 1, 1, so that's 2, and then A transpose 2, 1 is A 1, 2, which is 1. And then you kind of keep going and you get this. Another way to quickly do it is to take this first row and say this is my first column now. The second row is my second column now. It is the same definition. And if A transpose is equal to A, then we have a special name for that. A is a symmetric matrix. So for example, 1 and then all on the top left and all the rest are 0. Well, the transpose is exactly the same, which equals A, so A is a symmetric matrix. All right, so the next part is where we start to get more involved into our original application. So I started with transformations for this sole purpose because that is a very key component, it's a very, very visual component, and there's many applications to transformations of sets of data. Like addition and scalar multiplication only have like some certain limited application. So in order to talk about transformations, let's introduce a concept of matrix multiplication. So remember from previous like lectures or like videos to this, that if A is listed column-wise, so A1, A2, AN, where each one of these is a column, is not just an entry, then, so AI is the ith column of A. And then we can just talk about vectors for a moment instead of multiplying by a matrix. A vector is just a special matrix. It has only one column. And then we can multiply it, and then we get a linear combination of the columns where the weights are the entries of the vectors. So in this case, it would be x1, a1, which is the first column right here. And then you just keep on going in a corresponding fashion. Since this is not exactly a vector, you can't really say it's a dot product, but it's very similar to that concept. You can think of it as that concept if it helps you memorize. It's like if this were kind of a vector, it'd be a dot product of that. So x1, a1 plus xi, ai, all the way to xn, an. Similarly, if x has multiple columns, you just kind of take a matrix x. A matrix x. You take in the matrix x each column and just kind of correspondingly do it one by one to get the columns of the resultant. So this first column of x is going to give you a column in return if you multiply by that, and that'll be the first column of your resultant. Similarly, the second column of x multiplied by this will give you the second column of the resultant, and so on and so forth, and you can do this iteratively. Right, so the column of the resultant is equal to the vector produced by AX with the corresponding column. So in other words, the jth column of AX, which is the resultant matrix, is just equal to A times the jth column of X. And for this to occur, let's talk about it again. There's like n columns here, and then that means there must be n entries here so that you can have assign one to another. So you can have one-to-one assignment, basically. So as a result, each column must have n entries, and that means there must be n rows in X. So that means if A is an m by n matrix, then AX is a defined operation only if X is n by P. P can be anything, but n must be the same n as before. And then we will see later on that the resultant AX is going to have dimensions of m by P. So this column summation definition of matrix multiplication is a great way for theoretically understanding what kind of happens. What happens when you have some columns and then you want to add them up. So it's a good way to a good way, sorry about the zoom in, but it's a good way to talk about theory, like if you talk about vector spaces, you can have the columns sum up to be the vector space. But if you want to just kind of one by one multiply two matrices, it might be easier to have a second definition, since most of us cannot do several additions at once in our head and memorize that vector. Since that's what you're going to get if you're adding column vectors one by one. You're going to have to keep track of all the additions in your head, and that's difficult. We might want to do it term by term. So note that each entry of AX, at row I, column J, is by definition in the column of J, which means that column is A times the jth column of the original matrix X from previous definition, which then by definition is also that of the definition of multiplication. And then this, is the jth column of AX. And now we care about the ith row element. So for each one of these columns, since we adding is corresponding members, we're going to add the corresponding row. So that means you're going to have the row elements of each of A. So you have like these columns of A, and then you care about these row elements, and then only those row elements times the corresponding weights of A, so in that column. So what that ultimately is, if you look at this kind of mini proof, is these row elements are multiplied by these column elements in corresponding fashion, which is the dot product. And before we said it looked like the dot product, but in fact, that was, right here, that was a series of columns. But here, these are actually entries. So we can actually treat this exactly like a dot product. So each entry of AX is the row. So if the ijth entry of AX is row I, a dot product, column J of X. And that's an easy way to memorize like another iterative process where you go through each element. And so it's a more easy calculation. You can do it term by term. But you also have to note, this gives us another insight into kind of dimensions. Since you need to have row I of A, and A has m rows, and you need to have call J of X, and X has P columns, the resultant must be dimension m by P. And we can see this in an example. You see this 2, 3, -1, -1, 0, 1, 1, 1, 3, 0, 0, 2. And then if you kind of do the dot products, like 2 plus 9 minus 0, okay, so that's 11. And then 2 plus 0 minus 2, that's 0. -1 plus 0 plus 0, so that's -1. -1 plus 0 plus 2 is 1. That's a 2 by 2 matrix. So if you have 2 by 3 multiplied by 3 by 2, this is n, right? And then, so then you're going to have this as a resultant, m by p. So now let's go back to linear transformations now that we have defined these things and we can do something about them. Now we can define a linear transformation on the vector v as a matrix multiplication. So we're multiplying this matrix A by this vector v, and then we're going to have A as an m by m matrix as standard, and v is some vector. And in order to make this multiplication work, it must be m by 1. And it's by 1 because a vector is only one column, and it's a special type of matrix. So as a result, v is part of Rn. And we can say that. So now it's a domain. It's part of the domain of this transformation. And we need to now prove that this matrix multiplication, T, V, transforming V, equals AV, is in fact a linear transformation, right? And there's two cases that we need to prove. So first, we have to actually make sure that it is in fact linear when you multiply it. And second, we have to say, well, can any, like if you want to say a linear transformation is now matrix multiplication, you kind of need to say this works for all, all vectors, all transformations. And we're going to find out that we can actually, yes, describe every single transformation as a matrix multiplication. So let's go to the first proof. It might be kind of trivial, but if you have, AV is that by definition. Now we're going to go through the concepts of linearity. So if I have another vector W, then that's going to be that. If you plug it into the transformation, and I need to make sure it equals to TV plus TW. So let's just go through here, add corresponding terms. You get that, and then you get that. So this is just a real number. So we can just take this real number and multiply it by this column, and then the linear combination of this column, same definition. And we can split that up because this distributive property, right? And then we'll find out that that equals to AV plus AW, and then that's TV plus DW. So that condition of linearity holds. Now the second condition of linearity, we must have this scalar times V is equal to, you can just pull this scalar out, and now we're just going to go along with it, and that's equal to A times CV, which means every vector in, every element in this vector is multiplied by C, property of scalar multiplication, which means we're going to get this, and we can factor the C out now, which means we're basically pulling the C out of this transformation. So CAV, which is C times TV. And then that is our second and last condition of linearity. We can now conclude that matrix multiplication is indeed a linear transformation. Okay, sorry about that. The memory on the last video exceeded the phone's limit, so I had to re-upload. So yeah, let's just continue where we left off. We're here, we already proven that a matrix multiplication on a vector is indeed a linear transformation, and now we must show that every transformation can be reflected as a matrix multiplication. So first we have to give some kind of visual basis for it, and then we're going to say how we're going to describe this, transformation. So it's kind of hard to see, but right there. So we have, in this case, another rotation example where we have this vector v and we want to rotate it. So here's the xy plane. We rotate it theta degrees, and we're going to project it to have a z value of 1. So as you can imagine, the range of this projection or transformation is going to be z equals 1. The plane z equals 1 is parallel to the xy plane, if you can imagine that. And now, see, so that's the projection on the xy plane, and that's a theta degree rotation. So it's, it's kind of abstract, and it's kind of weird to say, oh, we have this this geometric set of instructions for visual instructions, but now how are we gonna so yeah, it looks like this, theta degrees and then 1. So how are we going to describe this as a form of matrix? Well, let's consider first a standard basis. This is basically, so when we write v equals that, like some elements, this is just 3, but it can be any, right? We generalize. That is just the weights of the coordinate vectors. That's what coordinate means. So, so if this were like 3, 2, for example, that means you have 3 on this side, which is just the x-axis, and then 1 on the y-axis. So that's what I mean by E1, E2. And basically, it's like 1, like the unit vector in that direction, the unit vector in that axis, and that is the standard basis. So we like that because now we can express whatever these values are as, let's say it's A1, A2. Now we can say V is A1, E1 plus A2, E2. That is a kind of definition of coordinates and the basis, so standard basis. We can always express a vector as some linear combination of the basis if it is in the of the same space. Here it's R2. So now we're going to transform that, and we're just going to follow the definition of linear transformation, and then we're going to end up with A1 times transform of E1, which is the first one, so the first unit vector here is 1, 0, and plus A2 times the transform of E2, which is 0, 1 by definition. And then we're going to see where that leads us, and basically we can see already this follows the form. Like transform of E1 is another vector. You take a vector and you output a vector, so this can be a column. And this can also be a column. So this just looks like matrix multiplication of a vector, and this vector is right there, and it's the same vector that we said right there, right? Because we assigned, we were going to say v equals like a1, a2 here. We assign these values, right, based on the basis. So the standard basis, that is. And we like to use that too, because when we transform it, it's very, we start from the axes. It's very simple to see where these axes are going to go. So we can do that if we can observe this pattern. And then that is just basically saying this is A now. This is V, and then this is A now. So then we can, so this is how V is normally written with this standard basis. So in general, V is that AN times EN, so if you're an RN. And then TV is we're going to expand it. And then that's going to be, in general, the transform of E1 all the way to EN, and then times A1 all the way to AN, so this is whatever vector you get in components. So then this is the A of the transformation. This is the transformation matrix, right? So then now we can easily calculate this too, because these are just the standard basis, and they only have one component in one direction, so you don't have to care about a bunch of stuff. And since that's easier to calculate, this is a very preferred method. So the column J of A is equal to EJ. So E is 4, then it's the fourth element of that vector is 1. And then that's how we get this matrix. So let's see some examples. Geometrically, we already talked about this rotation and increasing the height by 1. So the example we just did, so it's R2 to R3, which means N is 2, M is 3. So we're going to expect a 3 by 2 matrix. And let's just kind of go through it. So TE1, this vector, rotates theta degrees, like that, theta, and then you expand by 1, like that. So that means you're going to end up getting cosine theta, sine theta, by definition of the cosine theta, sine theta, and then 1, because it's always going to have 1. So that's the projection of your first standard basis. Now your second standard basis, which is just a y unit vector, rotate that as well. We're going to use some angle summation formulas to get negative sine theta, cosine theta, and 1. And we use the summation of pi over 2 because basically it's essentially the same thing. Except as the first one, except you rotate it pi over 2, right? Because the original bases are right angle apart. That's another property of standard bases that we like. And then we're going to get negative sine theta, cosine theta 1. So we can conclude that the matrix of transformation is going to be equal to cosine theta, sine theta 1, negative sine theta, cosine theta 1. Now let's look at some more examples. It's all really the same thing. If we want to reflect it over the x-axis, the x-axis remains unchanged because it's reflecting over itself, so that's still 1, 0. But then the y-axis goes to 0, negative 1. So then our matrix is 1, 0, 0, negative 1. All right, so these are kind of just powerful. They're just very simple too, right? As you can see that you just kind of see where these bases go. And then you can describe basically any time variant geometry if it gets more complex in the form of some vectors pointing to some points. And you can just, it's visual motion in space, and this is what we like. We like to see vectors going to other vectors and being able to describe it quite easily. And as an example, in the midterm when we were designing that 16A robot, this is basically all that it was testing. It was just testing transformations. Okay, so now let's look at more theoretical problems. So we want to find some matrix C where C equals V, and that means basically nothing is transformed, right? Because you're ending up with the same thing. And because nothing is transformed, the columns are just the standard bases. And we call this matrix I, the identity matrix, which means nothing's changing. And if you apply this column by column to some matrix A, you're going to see that each column remains the same, right? Each column is a vector, and then we already talked about how matrix multiplication is just column by column. So we're going to have I equals A, and then AI equals IA as well. We can see that just by doing some other redistribution of the dots of the rows and the columns. So this is a nice property, and this is a special matrix as a result. Yeah. So now let's look at some more engineering application. We're going to talk about the PageRank algorithm. This is an extremely simplified version, and it's very similar to the pump problem that we talked about. So 85% of browsers, this is an assumption that that's what they currently use. It's they're not really changing from that. 85% of browsers stop browsing at each discrete time step. Like we can choose this to be like maybe like 5 minutes, for example, before they click another link. So that's a good choice, right? Because like some people, eventually they go to work, or they're just done using the internet. Like no one's really going to stay on there forever, so we can't have a conservation of people on the internet. So we're gonna, and we can't just consider new ones either. We're just considering, the one group and where they're eventually going to end up. So since over time all these people are going to be gone anyways because of this 85% dampening factor, we're going to choose some discrete time, maybe an hour, like after an hour are these guys. Some guys are gone, but a good portion is still remaining if you use like 5 minutes as your discrete time interval. So every 5 minutes, 85% of the people remain. And then, so this is kind of like they gave this to us. Like normally you get this through like maybe experiment. And then yeah, so you can see that, let's basically see what this means. A loop means it goes to itself, which means like 65% of people originally A go back to itself, 0.1 go to C, and 0.1 go to page B. So that just means so 0.85 of the people go somewhere in the system, and that means the other 0.15 are just gone. This is our 85% dampening factor. And if you look at the outputs for each of them, you'll also see it's 0.85. So let's define a state vector ABC, which tells us how many people are at each page. And overall, at some interval that we choose, some time that we choose when it's gone, when it's ending, that's when we're going to see where most of the people are in pages. So in this one, since A has a lot of self-return and most of the other places you can see go to A, intuitive prediction would be A is the most important page. And it turns out if we do the math, it will turn out to be that way. I'm not going to do that since we already know how to multiply, but this is just a conceptual overview of our problem. So we are setting up this matrix, this state transition matrix it's called, and it goes from the column location to the row location. The reason that is because if you multiply this by the state matrix, you're going to have some combination of here, and then some combination from there, and some combination from here. So this is 0.65 times the amount in A, 0.25 times the amount in B, and 0.5 times the amount in C. And this is going to end up in your first row, right? Because we did our secondary definition of matrix multiplication, which is that it's row of the first one times the dot, the column of this. So they all end up in the first row. And that means it ends up in the A, wherever that is. And this is 0.65 of the amount in A, which is this column, 0.25 amount in B, which is this column, the B column, and 0.5 amount in the C column. So then we can see that this is a proportion from going from column location to row location. And notice that the column sum to 0.85 is the same thing that 0.85 from any place stay in the system, right? That's our assumption, and that, per time interval, and that's correct. So then let's do some preliminary setups. Okay, so a to the t plus 1 is, let's consider state transitions instead. So at any time, like maybe the first one, you multiply this by the original distribution, which is S naught, and that's your first time interval. And then you can do this multiple times. So the time 2 would be A times that. So that's A times this. And what do we call that? We call that, so let me write that and make it clear. A times this. All right? And then you can obviously, from this point now, just see, oh, you're multiplying A every time. which is a recursive process, and that is the recursive process of exponentiation. We're now going to define an exponentiation of a square matrix, because that way the dimensions are preserved, right? M by n multiplied by m by p is an m by p matrix, so you want a square matrix to preserve that. Now, that's just multiplying a by itself n times, as we might expect. Okay, so as a general formula then, s at some time interval is a to the t, like however many time intervals, right, times the initial state, and then we can choose some t, like an hour, so that, and if their discrete time interval is 5 minutes, and that's 12 discrete time intervals, so then we want to see S12, and then how many people are at the pages, and we can look at our state vector here and just kind of see which one is the largest, which A, B, or C entry is the largest, and then we're going to rank it. That's how we rank the pages, and that's a simplified version of the PageRank algorithm. And it all comes down from transforming some vector. Now, this is not some geometric basis, it's basis of data, but it's the same concept, and now you can hopefully see and appreciate how linear transformations are very integral in many parts of engineering. So thank you.